Hi, and welcome back to Advanced Machine Learning. I'm Victor Banks, and now we will talk about simple online learning algorithms as a follow-up to the previous lecture, where we have formalized the online learning problem and specified what the measure of quality is. But since now we haven't specified any online learning algorithm for an online learning problem, and this is what we will do now. And first of all, we will formalize how we can specify an online learning algorithm. Then we will look at one very simple online learning algorithm, namely the follow the leader algorithm. And then we will see that it works for a rather quite large class of online learning problems, namely the online quadratic optimization problems. So what we have done so far is we have specified the online learning problem. We had this basic online learning protocol and also the extended online learning protocol, but we haven't specified an online learning algorithm at all. And we can do this also mathematically via the following function A in the basic online learning protocol first. So we have here this basic online learning protocol where, remember, first the action is chosen by the algorithm and then the environment reveals an environmental data point. And now any online learning algorithm, which we simply call algo for short, can be specified now by the following mapping. So the mapping A, which is mapping a sequence of environmental data points and actions, where the sequence can vary. It can be of length up to time horizon, and it is mapping this sequence to an action, so to an element of our action space calligraphic A. And how this action is used can be seen here. So imagine we are in time step t+1, and then we simply plug in everything we have seen so far, so the full history of information, which is in time step t+1, of course, the very first environmental data point, also the first action we took, then the second one, and so on, till we arrive at the most recent pair of environmental data point and action. And this is plugged in this function A, and what we receive is another action, and this is the action the algorithm algo is using in time step t+1. So here we have implicitly also, or rather explicitly also, taken into account that this mapping A is also considering the loss. So the loss is essentially connected to our performance measure, the cumulative regret. So it's reasonable that the choice mechanism of any algorithm, any suitable algorithm, is also depending on the loss. So this is for the basic online learning protocol, and you might ask, well, how about the extended online learning protocol, where, remember, we have the scenario that the environmental data point consists of two parts, and the first part of the environmental data point is revealed before the action is performed. So what we can do then is extending, or rather adding to the full history of information, simply this first part of the current environmental data point if we are right now in time step t+1. So in time step t+1, before we make the action, we see this first part of the environmental data point, and we can take this into account to make an action. And you recall also that we want an online learning algorithm which is not using that much of resources, regarding memory and also time. So you might ask, well, is it really a good idea that we use here the entire information so far? Because this is somehow suggesting that our choice, our mechanism to choose the next action might also depend on the time. So what we look for is a mapping A such that we can express it or condense it rather to the most recent, so in the ideal case, the most recent pair of environmental data point and action. So that all we need to do to specify the next action is to plug in the most recent pair of environmental data point and action to get the next one, to get the next action. This is what we see here. Of course, it's also okay if we use not only the most recent, but perhaps the second most recent, so the pair in time step t-1, but we definitely don't want to use the entire information, because this is suggesting that this will be time consuming and resource consuming. And the very first and quite intuitive algorithm which you would think of for an online learning problem is the follow the leader algorithm, which is doing the following. So imagine you are in time step t, and now what you could do is you could keep track of the cumulative loss of all actions for the previously seen environmental data points. So you look at the cumulative loss of any action, and then what is a reasonable strategy to choose the next action? Well, you simply look at the one where this cumulative loss is the smallest. It might be that there are more than just one action which is having the smallest cumulative loss, and you just pick one of them. So this is why we have here an element sign. But in most cases it will be one action actually. So what you see here is, first of all, indeed something which is in line with our formalization. Namely, this here is a function which is depending actually only on the data points we have seen so far. So when we are in time step t, the data we have seen so far is z1 till zt-1, and well, here also the losses coming into play as we see here, right? That this mapping is also depending on the loss. But obviously the previous actions don't play a role actually, so all we need to keep track of is, or are, the environmental data points seen till time step t. And one artifact, let's say, of this basic online learning protocol is that we first choose an action and then only see the environmental data point. So in the very first time step we don't have any data, we don't have any environmental data point, so this sum here is void, and to make this well defined we simply say, well, we choose the first action arbitrarily. Yeah. So where does the name stem from of this follow the leader algorithm? So we can interpret this here as choosing the one which is leading in terms of the smallest cumulative loss, yeah, or error. So let's have a look at this picture here where we have 3 actions. We keep track of the cumulative loss. So this red action here starts with no loss, no loss, no loss. So it has the smallest cumulative loss so far. The green one started with a loss of 1 and then suffered no loss anymore. But still the red one will be preferred because it has a smaller cumulative loss. The blue one started with a loss of 2 and then a loss of 0. And then it might happen that the green one is suffering a loss of -1, so that its cumulative loss is jumping down to 0, but the red one in time step 4 is suffering a loss of 1, so its cumulative loss is jumping up to 1. So now you see the leader in terms of the cumulative loss is not the red action anymore, but the green one. And for the next 3 time steps, the green one will still be the leader, but then in the 7th time step, the red one is suffering a loss of -1, the green one a loss of +1, so that here again there's a change between the two. And well, at time step 8 and 9, so at 8 the blue action is suffering a loss of -2, so that the cumulative loss is jumping down to 0, and the green one stays with its cumulative loss of 1, and the red one is jumping up to 2 at time step 8, and so on. And then in the 10th, the red action is again the leader. So this is where the name stems from. You're picking the leader in terms of the smallest cumulative loss so far. And this is quite natural, especially if you look at the batch learning scenario where you do empirical risk minimization, because this is quite similar to what you do in empirical risk minimization. So in empirical risk minimization, this would be something similar to your empirical risk you have if you have seen t-1 data points, and then you are asking for, well, for these data points, what is the model in my model class? If we imagine that this action space A is a model class, which model has the smallest empirical risk? But exactly this point of view brings us to one issue of the follow the leader algorithm. Namely, we have here perhaps the problem that we cannot compute this minimizer quite quickly, because in the worst case, depends on our loss function, we have to check every action, which can be infinitely many, depends on our action space, and computing the one which is minimizing this cumulative loss can be time consuming and resource consuming. So we see in general this rule is problematic, because the longer we run this algorithm, the slower it will be, since this cumulative loss, keeping track of it, is growing over the time. Of course, in our example we saw before with the 3 actions, this was no problem. Only 3 actions, we can keep track of that. But if you have infinite many actions, this will be problematic. And in order to analyze this follow the leader algorithm, we will have a look at the following helpful lemma, which we'll use to derive theoretical guarantees. And it's stating the following. So imagine the sequence of actions used by the follow the leader algorithm, A1, A2, and so on, are denoted in this way for some arbitrary environmental data sequence Z1, Z2. So again, these are generated by the basic online learning protocol. So the environment generates data and the follow the leader algorithm is every time choosing the action or one of the actions with the smallest cumulative loss so far. And then we can state the following regarding the regret compared to some competing action A tilde. And this A tilde, this competing action A tilde, can be an arbitrary one in our action space. So recall what this regret was for the competing action A tilde. So we compare the cumulative loss of our algorithm for the environmental data sequence. And now we ask, well, what would have been the cumulative loss if we would have used this competing action A tilde throughout the time? And then we can show that this here is actually bounded by the cumulative loss of the follow the leader algorithm as it is, and the follow the leader algorithm, if we would know one data point in advance. So why in advance? Because here what we have is, recalling the definition, this is the minimizer of the cumulative loss in time step t. And the important thing is to note here we are looking also at the environmental data point in time step t, and we would use it here exactly in this case, although we would know it. So this is a theoretical consideration which will be helpful. And what this implies is in particular also a bound on the cumulative regret as it is. Well, because here this left-hand side is bounded by this right-hand side. The left-hand side depends on the A tilde, but the right-hand side is independent of A tilde, as we see. So what we can do in particular is we can look here at the supremum over all A tildes, all competing actions A tilde, because this here is true for all A tildes. And because the right-hand side is independent of A tilde, building the supremum on the right-hand side will not change anything. And well, this thing here, the supremum of the regret with respect to some competing action A tilde, this is how we have specified, in fact, the cumulative regret. So the overall cumulative regret, where we compare with the best action in hindsight. So the supremum here with the competing action A tilde will be attained by the best action in hindsight. So what is this telling us? It's telling us that the regret of the follow the leader algorithm, for any environmental data sequence, we have some environmental data sequence. We apply the follow the leader algorithm in the basic online learning protocol, and we can bound its regret always by its cumulative loss as it is, and subtract from there the one step look ahead cheater version of it. Yeah? So again, cheater, because this action here is using one environmental data point which this one here is not using. Yeah? So here we are only looking at the cumulative loss till time step t minus 1, because in time step t we only have this data. Yeah? But the t plus 1 follow the leader action rule would also include the environmental data point in time step t. All right, let's see how we can prove this. It's rather simple, and we make our life easier by forgetting that we have here this superscript, yeah, to denote that this sequence of actions is generated by the follow the leader algorithm. Yeah, we forget about the superscripts and only write these A1 and A2s, and we know that this is belonging to the follow the leader algorithm. Then all we need to show, yeah, is the following. So we want the regret of the follow the leader algorithm, which is by definition written down here. We want that this here is bounded by the difference of the cumulative loss of itself and this cheater version. Now the difference between its cumulative loss and its cheater version, yeah, where we have this 8t plus 1 here. And now we can simply look at these terms more exactly, and we see, okay, here this here and this here, they are the same. Yeah? So if we subtract on both sides the sum over them, yeah, they disappear. Now what we can do is we can bring the remaining sum on this side. It will end up on the right hand side, and this one we can bring on the left hand side, so it will show up on the left hand side. Yeah? So we have here replaced, yeah, equivalently rephrased our claim we want to show. Yeah, so all we need to show is essentially then that this inequality here is true for every competing action A tilde. And this can be done by induction over the time horizon t. Yeah? So remember, the time horizon can be also infinite. So we have here our short-term memory box where we remind ourselves how the action selection rule of the follow the leader algorithm is. So it's the minimizer or one of the minimizer of the cumulative loss we have suffered for all these actions. And well, what would be the initial step? In the induction, we assume that the time horizon is 1 and check whether this equivalent formulation is true. So what was the left hand side again? Yeah, so here the left hand side, we sum here over the cumulative loss of this cheater version. Well, if t is equal 1, then this sum here boils down to one summand, namely the one where the small t here is equal 1. So we have here the loss suffered by the action taken in time step 2 for the environmental data point in time step 1. But now our reminder comes into play. Now, how do we choose this action? Well, it's the argmin of the cumulative loss in time step 2. Well, in time step 2, the cumulative loss is only consisting of one loss, namely the one we suffered in time step 1, for seeing the environmental data point Z1, this one, and we look at the minimum one. But well, if we have now here in this case the minimizer, plugged in of the function we minimize, this is essentially what we have here, L of first argument Z1, and we plug in the first argument the minimizer of this thing with respect to the first input. Well, what will be the outcome? It's the minimum value of that. So we obtain then the minimum value. But the minimum value over all these actions is definitely smaller than or equal than the loss we would suffer for any other competing action A tilde. And this here in turn, this is nothing else than the cumulative loss the competing action would suffer for time horizon 1. Because in time horizon 1, this is only one loss in the cumulative loss. So we see in the initial step of the induction, everything is fine. We turn to the induction step. So we assume that this here is fulfilled for t minus 1, for the time horizon t minus 1. This inequality, this equivalent inequality we have derived before. And now we want to show that this here is implying also the inequality if we would replace here the t minus 1, the capital T minus 1 with t's. Okay, so then let's simply add on both sides of this inequality. So we are assuming that this inequality is true. On both sides we are adding now the loss suffered by the action of the follow the leader algorithm in time step t plus 1 for environmental data point zt. What do we get? Well, if we add it here on the left-hand side, what will happen? We can see, okay, we have here this additional term, but this left-hand side we end up with here can also be conveniently expressed as simply the cumulative loss of this one-step look-ahead cheetah version. So where we always are taking into account the environmental data point in the time step we are currently in. And if we add it to the right-hand side, well, it shows up on the right-hand side. So this is what we see then here. Okay, so we see here from the assumption we make, we can get to this inequality here. So we keep it in our short-term memory box. This is the reminder 1. This is exactly this inequality we have derived by adding this term here on both sides of the assumption for the induction step. And then again, we also remind ourselves of the action choice of the follow the leader algorithm. And well, now what we can do is we can use here in this inequality we got from the induction assumption, we can here use any A tilde we want. So remember this inequality here holds for any A tilde, for any competing action A tilde. And we now pick simply for our A tilde the action of the follow the leader algorithm in time step capital T plus 1. What do we get? Well, if we have here A tilde T plus 1, we can again write this quite conveniently into one term. So if A tilde is AT plus 1, this is boiling down to the cumulative loss of the action of the cheater version, which is using already the environmental data point in time step T, capital T, and we sum it here up to get its cumulative loss. Okay, but now our reminder number 2 comes into play, namely what is this action in time step capital T plus 1? It's the one minimizing the cumulative loss over all actions till time step including capital T plus 1. Again, what we see here is the same structure as in the induction step. So we are minimizing here some function which has a sum structure. So we are summing up here functions, loss functions, over these ZTs, and look for the minimizer in the first argument. And we plug in exactly the minimizer for this sum function. So what will be the result? Well, it will be the minimum of this sum function, equal to the minimum. And again, the minimizer of this sum function is definitely smaller than or equal than the sum function evaluated at any other A tilde. So we can plug in here any A tilde we want. This inequality here stays true. And this is all we wanted to show. So this is what we wanted to show, the cumulative loss of this cheater version. One step look at cheater version is smaller than or equal than the cumulative loss of any competing action. And we can use this result to derive theoretical guarantees in terms of the regret bound for the follow the leader algorithm. And one quite interesting problem are the online quadratic optimization problems, where quite generally we have here that the loss function is nothing else than the quadratic loss function we know from machine learning. So for an action A, AT when we are in time step T, and some environmental data point ZT when we are in time step T, we are looking simply at the quadratic or the Euclidean quadratic deviation between the two. Of course, to make this here well defined, we have to assume that both are the action and the environmental data points are vectors in the d-dimensional real-valued numbers. But you can also specify quite similar functions, loss functions, which are also having this quadratic penalization nature, as this quadratic loss function here. But we will only look at this very simple case because it's representative for more or less the others. And what we can show for the follow the leader algorithm is the following. So assuming we have an online quadratic optimization problem, where the loss function is of this kind. And we assume that the action space is corresponding to the RD. And additionally, the environmental data points are all living inside essentially a ball of radius v. So this here is telling us the largest z, the largest environmental data point z, which we can have, is such that its length, its Euclidean length is v. And in this scenario, we can use our helpful lemma, which we have proved previously, to derive that the regret of the follow the leader algorithm, no matter which environmental data sequence we will see, this regret will be bounded by some constant, which is depending on the v here, times logarithm of the time horizon plus 1. And why is this a good result? It's a good result because of 3 reasons. First of all, recalling what we wanted all the time, we wanted that the regret is sublinear with respect to the time horizon. But this thing here is definitely sublinear because it's only growing logarithmically. So we have here a logarithmic dependence on the time horizon. So it's the average regret. So if we would look at the average regret of the follow the leader algorithm divided by t, this will be definitely O in 1, going to 0 if it's only growing logarithmically. Also, the assumptions we have here, they are quite mild. So we only have this assumption that the largest environmental data point in terms of the length, Euclidean length, is bounded by v. This is not a too drastic assumption. And as you will see, and this is quite important, the action of the follow the leader algorithm in this case is nothing else than the empirical average over the environmental data points. This is due to the fact that we have here the quadratic loss function, and having in mind that this follow the leader algorithm is kind of also very simple to the risk minimization, empirical risk minimization, where we know from supervised learning that the model without a feature space is essentially the one which is looking at the empirical average over the data points, over the features.